about the uses of satellite data, we might think about climate change, for example, or air pollution, but there's also things like security and environment security. Tell me a little bit about that.
Yeah, this is a very interesting topic nowadays and becoming more important every day. And in Europe, I suppose that it started with EUMETSAT eruption in 2010.
Which
already.
was the big Icelandic volcano.
Yeah, big Icelandic. We closed the airspace completely. And at that time, it was realized that real-time monitoring is really needed. Upper left, we have Kasatochi volcano eruption, which happened 2008, and SO2 coming from this volcano. And we can see the long transportation. It spreads from Aleutian Islands to Europe.
So this is sulfur dioxide, so the gas that's coming out of the volcano.
Yeah. It released quite a lot of SO2 into upper atmosphere in stratosphere, and this is good example of long-range transportation which happens in atmosphere. And so because this SO2 cloud, it reached Europe.
So even though the volcano itself was on the border between Canada and Russia, it was a long way away, you know, there's one atmosphere, and all these things get shared.
That's true. This is the recent Vanuatu eruption in 2008, and this is also SO2, sulfur dioxide. And we can see how the SO2 cloud spreads from Vanuatu, and there's several eruptions going on. First, we see something, then there are some days we cannot see anything, and it repeats itself. So this is one example of long-term degassing of volcanoes, which happens all the time. Although in this case we had some real eruptions also releasing some aerosols, volcanic dust.
So there's a difference between the volcano just quietly, you know, just gases coming out, but it doesn't look like anything's happening, and then you get the big eruptions.
Yes.
And this has been really important recently, hasn't it? Because the Vanuatu government has been moving people away from some islands because of these eruptions, and they'll be using data like this.
I hope that they are using this kind of data. If we have something like Vanuatu, we know the situation very well because the people are living there and it's small island only. And there's no other countries nearby which could be affected, in fact. But the situation is very different if we have Icelandic volcano erupting, because what is the worst one is this volcanic ash. If it spreads to Europe, it may affect to flights, for example, or economical conditions.
So there's a whole, even though it's just one volcano a long way away, you can follow it downstream, and it affects more and more as it goes.
Yeah.
And how about these two on the bottom here?
Here we have a EAC animation. First, this one, which is EAC ash index. This is Kalpuko eruption in 2015, and we see volcanic aerosols, which is volcanic ash, spreading from Chile to Atlantic Ocean.
And were these high up in the atmosphere, or were they low down where, you know, a citizen might notice them?
These are quite high, in fact. Although in this case we had also low-level aerosols coming, which affected to southern Brasilia, for example. They were seen in ground level at that time. But these are quite high level, and this is also the reason why they are traveling so long distances. Because if the ash is near the ground level, it usually deposits quite soon.
So there's a difference, but the place where the ash starts off in the atmosphere makes a difference to where it travels to.
Yes, the plume height is very important, and it's also very important to know for modeling, because the one input source for modelers who is using this kind of data is what is the plume height, what is the injection height for volcanic ash.
And how good are these satellites at that? Because, you know, their satellites are up and they're looking down through the atmosphere. How good, you know, GOME and EASI, how good are they at knowing where it was in the atmosphere?
Not very good. Of course, LiDARs and this kind of ground-based instruments, they are much better. I hope that in future this situation will be improved. But already we are getting quite interesting results with COM2 and EASI. We will release plume height products for both of those instruments later on within this ACSAF period.
So the satellites are the same, but your analysis is getting better?
Yeah, analysis is getting better, and all the algorithms which we are using, we are continuously developing them and taking new scientific input from other sources too. We are not just using expertise in our team, but we are also using other scientific information and knowledge.
And how about this last one down there?
The last one is one example of SO2 release within 1 year. This was 2011, and we can see ERC measurements, ERC SO2 measurements, and we have NAPRO in Africa, which released quite huge amounts of SO2 over a long period. And then we have Grímsvötn eruption in Iceland, and that SO2 cloud. And the last one is this sea layer erupting volcano.
And the interesting thing here is you can see it doesn't go in a straight line.
Yeah.
The path that gas travels is, you wouldn't necessarily expect that.
Yeah, because the gases as well as aerosol, they follow the air currents.
What we've got here is a picture of a representation of an event that happened in 1982, and this was where your field got started. Tell me about what happened.
Yeah, exactly. In fact, the story began in 1982 when a British Airways aircraft flew into a cloud of volcanic ash over Indonesia and lost its 4 engines.
Which is a huge event. You're flying in a plane a long way up in the sky, 4 engines gone.
Yeah, really. The volcanic ash was thrown up in the atmosphere by the Mount Galunggung. It's an Indonesian volcano located in the southeast of Jakarta. And so, after losing its 4 engines, the plane was diverted to Jakarta airport in the hope that enough engines could be restarted. And finally, the planes succeeded in gliding out the volcanic ash cloud, and all engines were restarted and allows the plane to safely land at the Jakarta airport.
So it had a happy ending, but there was a very frightening moment when they could have lost the plane just because of volcanic ash.
Yeah, this incident made the aeronautical community realize the danger of volcanic ash for aviation.
And what's volcanic ash like? Why does it cause problems for aircraft?
Well, in fact, volcanic ash is composed of silicates and is also made of very abrasive particles which can damage aircraft engines when they are injected into engine.
The ash particle here, it's basically glass, very sharp, hard glass, and it's flying through a jet engine which has a lot of moving parts. It's a very dangerous situation.
Yeah, that's right. Because the ash particles have a temperature, a melting temperature, which is about 1,100 degrees Celsius, which is very close of the aircraft engine temperatures. So ash particles can quickly melt in the engine and so accumulate as a resolidified component in the cooler parts of the engines and so damage the engine.
And so it was understood that we needed to study these volcanic ash particles, and the important thing is, what sort of ash is it and where does it go? So 35 years on, what's the system now for monitoring this and what do we understand?
Yeah, with the occurrence of numerous ash encounters by aircraft, the ICAO, International Civil Aviation Organization, decided to set up a global watch for volcanic ash. And so, therefore, 9 volcanic ash advisory centers, called also VAACs, were created in the 1990s in order to watch over volcanic activity over the world.
So these are the 9 here. So they divided up the world, and you've got one of those centres here in Toulouse. So what region are you responsible for?
Well, Météo France, the French National Weather Service in Toulouse, is in charge of the Toulouse VAAC, and the Toulouse VAAC is in charge of a very large region extending from Western Europe to Asia and also including Africa.
And where are the volcanoes in that area?
Well, the most active volcanoes in the area are located in Italy, for instance, Mount Etna volcano, but also the volcanoes located in the Naples region.
And once you have an eruption, where can the ash go? How far does it travel?
The volcanic ash can travel very far from the volcanoes, about more than 1,000 kilometers, and so it can stay in the atmosphere for days, for instance, or longer.
And is the ash from all volcanoes the same, or do different volcanoes put different things into the atmosphere?
Yeah, volcanic ash can vary from one volcano to another, but this composition of ash is not taken into account by the numerical models.
Tell me a little bit about what the Volcanic Ash Advisory Centre and the London branch of it is for.
Okay, in fact, London is responsible for forecasting where the ash from volcanoes in the northeast Atlantic that are erupting, for forecasting where the ash goes. So that includes Iceland and a little tiny island called Jan Mayen, which is about, I think, about 1,000 kilometres to the north of Iceland as well.
So you've got some LiDAR. Tell me about the role of LiDAR in monitoring volcanic ash.
Back in 2010, one of the biggest challenges we had was actually, obviously the forecasting was a big challenge, but also the observing, the monitoring of where the ash was as it moved across the UK. I mean, it's not conventional weather type stuff, it's an aerosol in the atmosphere. So we were able to use laser cloud-based recorders, which are conventional ways of measuring how high the clouds are, retuning those to give us an idea, but only at very, very low levels. So it was conceived that it would be a good idea to do something a bit more elaborate, and the UK government brought us some very nice new LiDAR. They're research grade instrumentation, so a little bit temperamental. It's taken us a little bit of time to actually get our heads around how to use them. But what they can do is observe layers of ash and other aerosols up to sort of cruise levels of the aircraft, right up to sort of 40,000 feet across the UK. So we can now see where the ash is in great detail from the ground upwards, which is great because obviously what the satellites can do is to see what's going on with the ash from space downwards. So it really does complement the existing capabilities that we've got.
So where are the LiDAR? How many of them are there?
We've got 9 LiDAR dotted around the United Kingdom. They are geographically spaced to give us a good sort of strategic idea. So furthest north is up in Lerwick, up in the Shetland Islands. Furthest south is down in Campbell and down in the far southwest. And the others are sort of dotted around at various places in between. We've even got one on the back of a wagon. So we can actually redeploy that one as needs arise.
And have you had much practice with them? Because obviously the Icelandic volcano in 2010 was the big event, but we haven't had so many eruptions since then. So has it ever been tested as a system?
The way we've tested it as a system is to use dust from the Sahara as a proxy for that. There's been several events like that. We also tested it during the Portuguese fires. We were able to see layers of aerosol coming up across the United Kingdom during that. And what we're actually looking to do with that is when we need to switch them on, because they're a bit sensitive, we can't have them on 24 hours a day. And actually using it as a way of how we teach our forecasters to actually look at difference between dust and ash and aerosol particles, which look completely different from water particles that we would see in cloud.
Tell me a bit how that measurement fits in with the rest of the system, because it's not just one volcanic ash advisory centre in one place. There's a huge network and a big international effort. So those LiDAR measurements, how do they feed into the rest of that system? What happens next?
Well, we put it onto our website. At the moment, we don't share the data, as it were, so it's not raw data that we share, but the website and the the thumbnails, as it were, of those ash in real time, what we detect using the LiDAR, is available to anybody in the world sort of logging on to the website. And we've worked very closely with partners around Europe to sort of make up a patchwork of cloud-based recorders which have been retuned to look for ash, and also research-based LiDAR in many parts of Europe and other parts of the world as well. It's been really, really interesting because it's been about sort of starting from scratch and coming up with a new observing network for observing aerosol up there in the atmosphere.
And how does that fit in with modelling and the services that are available as a result of all that?
That is the next big challenge, if I was honest. So for satellite imagery, we can assimilate satellite imagery of where ash is now to give us a better source term for volcanoes. Certainly we can do that at the Met Office to give us a better definition of what the volcano is doing at source, because that's fundamental to forecasting. We're using those techniques now to actually try and integrate some of the LiDAR information that we've got available to us as well. The technique is called inverse modelling, so it's like, this is where the ash is, and we've run it backwards to actually give us an idea of where it must have come from to end up where it was, as it were. And at the moment, those techniques are based on sort of those dust and sand proxies that I talked about, because we haven't had much ash to play with over the last 6 or 7 years.
It's probably more comfortable for everyone that way. And how about the international cooperation? So you've got lots of organisations, there's obviously lots of interest from the aviation industry especially, but you've got national governments and national meteorological organisations and this huge web of people. How easy is it to get all of those to work together?
It's a big challenge. One of the things about being a weatherman, a national Met Service, is that you can't do the weather without collaborating with everybody around the world. So what's going on in the Pacific Ocean will have an impact eventually on what goes on over Europe and the UK and even down at the local scale in London. We've had to mimic that sort of approach, that integrated approach, with lots and lots of stakeholders, in the Met community, but with academia and the private sector. And that's come up with new challenges because, us guys in atmospheric composition and the Met Service world, we're very used to collaborating, sharing data, getting it around in near real time, understanding what it actually means. Bringing new partners on board, from academia and the private sector has been a challenge, and working out how all that works to actually deliver on what is an operational capability. It's not research that you can spend years and years developing and look at the results and what have you. When these things happen, our customers expect results very, very quickly, and customers, governments, the airlines, and indeed the public.
And what's the role of the World Meteorological Organization in all of this?
So WMO is the UN body for weather, climate and water, and what they maintain are the networks, or if you like, the forum for us all to come together, 191 nations around the world to come together and talk about the weather, atmospheric composition, hydrology. They look after the science, they look after the observations, and a lot of the sort of expertise and collaboration that we depend on to do our everyday work in the weather and the water sort of sectors, and increasingly with the atmospheric composition as well. So they're a fundamental part of the deal, as it were, and they also have this working relationship with the International Civil Aviation Organisation, where ICAO say, we need this to happen, you're the clever guys with all the science and the technical expertise, you come up with solutions to actually respond to our requirements. So they're a big and significant player.